If you can find a place where there's better Wi-Fi, that might help. Okay, it's 8 o'clock. Wondering what something means up here on my Zoom screen. Let's see. I have graded your exams, most of them. I'll be getting those back to you today. I was a little disappointed. Some people did quite well, but a lot of people did not. Also, I counted off if you did not show your work. I don't know how you come up with the derivative and the second derivative of x squared over x squared plus 3 without doing any work. I can't. So I counted off for things like that. If stuff just appears on your page, even if it's correct, and you didn't show me that you understand how to get there, lots of points got deducted. Well, some of you also did a nice job of explaining what you were doing, okay? A lot of you doing better with that. But yeah, there were A's and B's and C's, and there were also a lot of D's and F's. So, well, I haven't really compiled any averages or anything, but I'll be doing that today. It's pretty much just my impression from grading them yesterday. The solutions have been posted, so you might want to check those out. You have homework due this weekend, okay? So make sure you get that in. And of course, you'll get another assignment for next week. I'll be putting that together over the weekend. Okay, any questions? All righty, then I'm gonna start talking about exponentials and logs again. Okay. Okay, well, I was thinking I would go ahead and talk about other bases. If you don't know what that means, that's okay. Okay. But then I thought, well, maybe I should just stick with these two functions we've now defined and have been talking about all week and show you what we can do now that we could not do before. Okay. These are two very important functions, the natural logarithm that one, and this is exponential, and I guess this should be the natural exponential too. I'll show you what's natural about it next week. Okay, you want to keep pictures of these functions in your mind, okay? Log crosses the x-axis at 1, is increasing, has domain, the positive reals. It's got vertical asymptote, then the negative y-axis, and then it increases without bound as x goes to infinity. And the exponential function is the inverse function of the natural log. Basically, you just take the diagonal line and flip the log over it. So since the log has vertical asymptote, the negative y-axis, that's going to make the negative x-axis an asymptote for e to the x, and that point is 1, 0, 1. Okay. The exponential function also increases without bound, and it has domain all the reals and range the positive reals. The range of the log function is all the reals. So because they are inverses, the domain of one is the range of the other. Okay, so what can we do with these? Well, I started working this problem, probably last week. Suppose you want an antiderivative for the tangent function. And then I stopped because I realized you had to know about logs before you could do that. Okay, so this is equal to, well, the tangent is the sine over the cosine. And then I can use a u substitution. Somebody came in. So I'm going to let u equal to the cosine of x. If I do that, du is minus the sine of x dx. And that turns my integral then into, okay, well, so minus du is the sine of x dx. And that's minus du. Okay, that replaces the sine of x dx part. And then we've got that 1 over cosine, that's 1 over u. Well, we just learned antiderivative of 1 over u du is natural log of u. And u is equal to the cosine. So and you can leave it like that, or you can use the properties of logarithms to put that -1 inside. Okay, remember we have this property ln of a to the r is r ln of a. So this is really -1, and I'm just taking this and turning it into that. And that's ln of the secant. And actually, okay, that's not the most general antiderivative. The most general antiderivative is this, absolute value of u. So absolute value there and absolute value there. And let me show you why that's so in just a minute. But first, any questions? Can you all hear me?
Yes, ma'am.
Okay, and you can see my
Excuse me.
screen.
Excuse me,
Yeah.
Miss Kenny. I do have a question. You get the negative sine x from the antiderivative of cos, right?
Right.
Okay. That's it.
Well, no, the derivative of cosine is minus the sine.
Oh, okay.
Okay. The antiderivative of the cosine is plus the sine.
Okay.
Okay.
Thanks. I got it.
Okay. All right. Well, let me show you why the most general antiderivative of 1 over x dx. Okay. ln of the absolute value of x. Whenever we do antiderivatives, we're assuming that we're talking about some interval, okay? You're not allowed to hop over discontinuities generally with integrals. Okay. Situation's a little more complicated than that. Actually, jump discontinuities, a finite number of jump discontinuities, okay, but you can't jump over an asymptote, whatever that means. All right, so let me just explain this. We have the natural log function. And I'll put that on here. That is, what did I do? ln of x. Okay, so what is this function ln of the absolute value of x? This is a composite function. The inside part is the absolute value. That's the inside function. The outside function is the natural log. So what is this? This would be, break it up, ln of x if x is greater than 0, because the absolute value of x is x if x is positive, and it is ln of minus x if x is less than 0. Okay, because let's write that down for handy reference. Absolute value of x is x. If x is positive, it's minus x if x is negative. And of course, the absolute value of x is defined at 0. However, the log function is not. So what does that say? Well, that says that when I go over, look, here's 1, 0. Okay, if I go to minus 1 over there on the x-axis, and I'm just talking about the x-axis, so why don't I just leave that? Okay. Well, the ln, so it'd be, why is my pen not working all of a sudden? Excuse me. Let me dock for a minute. Okay, this usually works. Yeah, okay. Now go back and back. All right, so ln of the absolute value of minus 1 is ln of minus 1 is ln of 1 is 0. Okay, so that point there is on the graph of ln of the absolute value of x. If I take, well, any number, it's okay right there, then my picture, it's got that natural log. Well, it's corresponding point on the, so this is the number a, and this would be minus a. I'm going to get the same natural log, okay, for a positive, and then ln of the absolute value of A, let me not write that. Okay, ln of the absolute value of minus A then is going to be ln of A. Because if A is positive, then minus A is negative. But the absolute value of minus A is A. And so I'm going to get the same log. And that means that ln of the absolute value of X is going to be this curve reflected about the y-axis, okay? So it's just going to look like that. So that composite function has a bigger domain than the log function. The domain of is is all non-zero real numbers. So it sort of extends the log function. Notice there's still no way to define this thing at 0 because you've got a vertical asymptote there, and you can't just jump over vertical asymptotes. But we do have that extension, so that's why the most general antiderivative of the tangent then is going to be ln of the secant, or minus ln of the absolute value of the secant, or minus ln of the absolute value of the cosine. I don't know what that is. Okay. Questions, anybody?
Did you say the natural log has a bigger domain than the the natural log of absolute X has a bigger domain?
Yeah. Right. The domain of the natural log of the absolute value of X, this is a composite function. Absolute value of X is the inside function, log is the outside function. And my pen is kicked out again. Oh, no, I just have the eraser. Okay. Yeah, the domain of the natural log function, so without that absolute value inside, is still all positive numbers. Okay. So this function has a larger domain than that function does. Okay, let's see. Oh, I have a bunch of problems here. I'm just gonna go through. Let's see if I can find those. Well, we've been doing integrals, so why don't I do some integrals first? And we're going to, now that we have the natural log function, the exponential function, and
How many calories does that have?
160.
How much protein does that have?
somebody's microphone. Okay. Losing my track of myself. How about this one? Yeah, it's got the log in it. Yeah, we're going to, now that we have these functions, we can integrate them, we can differentiate them, we can just combine them with other functions. We can graph them. Okay, we'll do some of those day 2. But I want the antiderivative of 1 over x ln of x. Would anybody like to suggest something before I do it? What do you think would work here? Maybe that's not fair. Okay. Well, what I see when I look at this thing, I've got the natural log function in there, and I've got the derivative of the natural log function in there. So how about a u substitution? If I let u equal to ln of x, then du is going to be 1 over x dx. And that looks like I'm set up very well for that. So I've got 1, let's see, that 1 over x dx, that becomes du. And the ln of x is u. And the antiderivative of 1 over u is ln of the absolute value of u. Okay. Again, that's that more general form. And let's see. U is ln of x. So it's ln of the absolute value of ln of x for the antiderivative. Oh, that beeping is my stove. Ignore it. I set it to clean itself this morning. Okay, how about an exponential? Remember the derivative? Well, I want to scroll way back up there. Okay. The derivative of e to the x is e to the x. We showed that yesterday. That function is its own derivative. Okay, if you look at this, the derivative of 1 plus e to the x will be the derivative of 1 plus the derivative of e to the x. The derivative of 1 is 0. The derivative of e to the x is e to the x. So a u substitution would work here too. Yeah. So du would be e to the x dx. That changes this problem to the square root of u du. And that is the integral of u to the 1/2. That is not part of my computation. And that's u to the 3/2 divided by 3/2. So that's 2/3. And then u was equal to e to the x plus 1. Oops. Okay. So we have that antiderivative. I'm looking for some more problems. How about this one? Any question about that one before I go on? Okay. What about this one? This is a definite integral. 0 to 5, 2 e to the x plus 4 cosine of x dx. Okay. This one, U substitution is not going to help me with this one. And in fact, I don't really, this is pretty straightforward anyway. I've got the sum of two functions in there. So I can break it into the sum of two integrals. And that's equal to 2. Okay, bring the constant out. That's, yeah, this is a property of integrals. And this, but the fact that I can bring out that 2 and bring out that 4, that's another property of integrals. Okay. And then, well, the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x. So this is 2 e to the x. I want to evaluate it from 0 to 5. Plus 4. Antiderivative of the cosine is plus the sine. And we wind up with 2. Okay, use a fundamental theorem, e to the 5th. Well, I used it right there, actually. Now I'm just evaluating f of b minus f of a, that thing. Plus 4. And, okay, I'm just going to leave that as e to the 5th. E to the 0 is 1. And I'm going to leave that sine of 5 is just sine of 5. Okay, that's not a special angle or anything, but it's a perfectly good number. Sine of 0 is 0, so I can just leave that off. Yeah, sine of 5 is a good number. I mean, e to the 5th, good number. Okay, pi squared, good number. And leaving your numbers that way, I prefer. I do not like getting approximations. Sometimes all you got is approximations. And sometimes you want to know how big a number is. And you need an approximation for that. But you're throwing away stuff whenever you turn an exact number into an approximate number. Okay. Let me pick out another one. How about this one? I should do some derivatives too. Y 5y to the 7th over y squared dy. Okay. Well, okay. I don't think a U substitution would help here. I don't see a function and its derivative sitting in there for me. But I don't need a U substitution. I can rewrite this function inside that I'm trying to integrate as, okay, y over y squared plus 5y to the 7th over y squared. And that's equal to, okay, oops, forgot my dy. No, I didn't. That's still all inside that integral. Okay. There. Okay. All right. So that's then 1 over y dy, simplifying that y over y squared. And also breaking it into sum of two integrals. And I'm going to do, I can bring the 5 out. And then y to the 7th over y squared is y to the 5th. So I changed this problem into this problem. Both of those are now doable. Any derivative of 1 over y, ln of the absolute value of y, and then prime plus 5, and then any derivative for y to the 5th, y to the 6th over 6. Okay, so that's a few problems involving integrals involving logs and exponentials. Let's do some derivatives. Differentiate this function, the log of the sine of x. Okay, well, that's a composite function. The outside function is ln, and I'll call it u. And the inside is the sine of x. Okay. So f prime of x is going to be I should do another, I'll put some more stuff. Okay, so the derivative of ln of u, 1 over u, the derivative of the sine of x is the cosine of x. Okay, and f prime then is 1 over u times the cosine of x, right? That derivative of the outside function applied to the inside function. That's what that 1 over u is. And u is the log. No, u is the sine, excuse me. Okay. Okay. U is, stop that. U is the sine, so that's 1 over the sine of x times the cosine of x, which is the cotangent of x. Well, let's do several of these. What if I switch the inside and the outside? So now let's differentiate the sine of the log. Now my outside is the sine, and my inside is the log function. So derivative of the sine of u is the cosine of u. Derivative of the natural log of x is 1 over x. So this one would be cosine of u times 1 over x. So yeah, the derivative of the outside function applied to the inside function times the derivative of the inside function. Then going back to the x's. And I would put some more parentheses so it's clear what the cosine applies to. Any question about either one of those?
I have a question, but I'm waiting till the end of the class once we're finished because it has more to do with one of the homework problems.
All right. All right. Okay. Well, let's try another combination. How about I define g of x to be sine of x times the log of x. Now that's a product of two functions. Okay. This is a composite of two functions. And my pen, there we go. Composite, this is a composite. The inside and the outside flip between A and B. And of course you get different derivatives when you do that because it matters what the inside function and what the outside function are. Okay, sine of x times log of x, if I want g prime, I have to use the product rule. Okay. Because it's a product of two functions. Product rule says that this is the cosine of x times ln of x. So derivative of the sines, cosine, times the ln plus, and then the sine of x times the derivative of the log of x. And I would just leave it like that. I don't think there is a simpler way to write it. How about this one? F of x is the natural log of x plus 1 over the square root of x minus 2. And I want the derivative again. Actually, there are two ways I could approach this. Yeah, let me show you both ways. I can view this as a composite function. Okay, so one way. I've got the outside function, ln of u, the inside function, x plus 1 over the square root of x minus 2. So the derivative of ln of u with respect to u is 1 over u. The derivative of x plus 1 over the square root of x minus 2. Well, let's see. I'm going to have to do a little bit of work for that. I need the quotient rule. And I've also, let's see, before I do that, why not? Well, if I write that as x minus 2 to the minus 1/2, then I could just use the product rule. Okay. So I'm going to change the form of this function that I'm differentiating first. But I've still got some work to do. Okay, so this is equal to the derivative of x plus 1 times x minus 2 to the minus 1/2 plus x plus 1. I didn't leave enough room. Okay. X plus 1 times, okay, I have to use a chain rule on that x minus 2 to the minus 1/2. The inside function is x minus 2. The outside function is raising something to the minus 1/2. That's going to be minus 1/2 x minus 2 to the minus 3/2. And then the derivative of x minus 2 is just 1. Okay, so let's write all that out again. Okay, well, I've got minus 1/2 there. So we put a minus. Yeah, minus.
Shouldn't that 1/2 in first power be negative?
Oh, what? Wait a minute. Let me just finish my thought, and then I'll see. Okay. Okay, Mr. Libby, what was your question? And what are you saying?
On the first part of the equation you just wrote down, you put
Oh, yeah.
x minus 2 to...
Yes, you're right.
Okay, thank you.
Thank you. Okay, so that's a pretty complicated looking derivative. Shall I? Let's see. Well, let's just leave it like that for the moment. Yeah, but it is the derivative. So what is f prime? Now, we were just taking the derivative of that function. That's the inside function. So f prime is going to be, okay, the derivative of the outside function, so that's 1/u, times the derivative of the outside function applied to the inside function, that's 1/u, times the derivative of the inside function. And the derivative of the inside function we just computed. Okay. And that's equal to, okay, well, what was u? That is 1/x plus 1 divided by the square root of x minus 2 times x minus 2 to the minus 1/2 minus x plus 1 times x minus 2 to the minus 3/2 u. Okay. That's really messy. Let's simplify. Let me just try to write it in a nicer form. I mean, sometimes they just are messes, and you have to live with it. But let's see if I can improve on this somewhat. For one thing, I've got 1/a over b. And I can think of that one as being 1/1, so that's going to be equal to b over a. Right, so I could write this first part as the square root of x minus 2 over x plus 1. And then let's take those back to the square root thing and put them in the denominator. X minus 2 to the plus 3/2. Okay, so that's equal to, well, if I expand x square root over square root there, So that would be 1 over x plus 1. And then also this times this. Okay. Well, the x plus 1, that's going to cancel with that. And then I've got a square root here and raised to the 3 halves there. And that's also supposed to be a minus. Okay, so let me just write this. Well, okay, square root of x minus 2 is x minus 2 to the 1/2. So this winds up being 1 over x plus 1 minus, okay, 3 halves minus 1/2 is 1. No. So this winds up being that. I think I left out a half. Oh, I did. Okay, sorry. This is supposed to be over 2. I forgot that little 1/2 there. So that's over 2. So that's over 2. And there's a 2 there. And a 2 there. And a 2 there. But that looks a lot nicer. All right. Okay. Well, that was one way to do it. Just viewing it as a strict composite function. Okay. But there's another way. ln of x plus 1 over the square root of x minus 2. We have this rule about logarithms that says ln of a over b is ln of a minus ln of b. So I can use that to write this as ln of x plus 1 minus the natural log of the square root of x minus 2. And, okay, and I can go further. That square root is really x minus 2 to the 1/2, okay? And then I can use that other rule, the one that says ln of a to the r is r ln of a. I can bring that 1/2 down. This is ln of x plus 1 minus 1/2 ln of x minus 2. Now, I have not differentiated yet, okay? I just rewritten the function using the rules of logarithms. Yeah, logarithms are the only functions that have these nice properties, these nice algebraic properties. But it does apply here. And actually, this is easier to differentiate than this is, as we just saw above, okay? Yeah, because that inside function had a pretty messy derivative. But this one, okay, then f prime, which is the derivative of this. Because this is that original function. This is, yeah, ln of that. This is that. So they're just written in different ways. So this is easier to differentiate. The derivative of ln of x plus 1, well, that's actually a composite too. The inside function is x plus 1, the outside function ln. So this derivative, and then u prime is 1. Okay. So, and you probably do this in your head, in fact. It's going to be 1 over u times 1, which is 1 over x plus 1. And same way, the derivative of ln of x minus 2, 1 over x minus 2 times 1. Okay, so the derivative of f then is 1 over x plus 1 minus, looking up here, minus 1/2 times 1 over x minus 2. That was much easier than the other way. Well, we got the same thing both ways. So yeah, the natural logs, that this is going to give you, in some problems, a better option for how to write your function, because the log does have these nice algebraic properties. Oh gosh, how am I doing? Oh, pretty much out of time. Okay, well, this is probably a good stopping place. Question, anybody got a question on this problem?
No, but once again, I have a question on F of the homework.
Okay, well, we'll hold that until later. Okay, so yeah, the first way I worked it was not the easiest, but we could do it with persistence. Okay, and once you've got that messy answer, yeah, I did a lot of algebra to make it look nicer and wound up with that. But the other way takes you pretty much straight to that easier way of writing it. Okay, well, happy Friday, everybody, and have a nice weekend. Hang around if you've got a question. I know you do, Mr. Drake. Okay. Otherwise, you may leave.
Have a good week.